Well, in this segment, we'll look at some of the properties of bra and ket vectors in this new formalism. And what I'll do is I'll just list them, and then maybe we'll come back and, as time permits, and show how some of these quantities arise. Um, First thing is that for every ket vector, here I've got alpha as the sort of the label of it. This would be like alpha vector in a certain sense. Every ket vector has a corresponding bra vector that carries really the same amount of information in both. And if you remember, the ket vector uh, here is related to the bra vector, and that the Hermitian conjugate of the ket vector is just the bra vector. And by that I mean you for this dagger, you take the complex conjugate and the transpose. Uh, it's sort of an oddity of, well, maybe not an oddity, but it is a characteristic of quantum mechanics that it really isn't a vector that's important, but is more of a ray. A ray is, if you have a vector and you multiply it times a scalar, then you basically have an adjustable length vector. And for quantum mechanics, really any length of the vector corresponds to the corresponding of the ket vector corresponds to the same quantum state. And so it's useful to introduce this scaling factor. Lambda here is a complex, and thought of as a complex number, and this lambda times psi is a state of the system. And so the ket vector of lambda psi, I can bring this lambda, this complex number outside. On the other hand, if I have a bra vector, then I can certainly form the bra vector corresponding to this state. It's just lambda times psi bra vector. And in that case, because of that complex conjugation relationship up here, one can pull outside uh, the lambda, this constant. It could be a complex constant, and so in general, you'd take the complex conjugate of it because of the star operation in our definition of the ket and the bra from the ket. Uh, Another thing that it really doesn't matter which side I put this on, and I can put it on this side, and sometimes you see that, and then or you can put it on this side. If you look at the properties of these, what you find is that if I take psi two states and form their inner product, I form the bracket of this ket and this bra. That's equal to, well, it turns into a number. This is really just like an inner product, so it turns into a number which is generally a complex number. And if I reverse the order and do psi and phi, then this complex number, it turns out, when I reverse the order, is just the complex conjugate of this one. So that's another relation. That may be one we'll show a little later. The bracket is a linear in a certain sense. It certainly is in this direction. If I add two quantum states, well, that's another quantum state. So I'll have a complex conjugate, a complex number times a state plus another complex number times a state. Then I can do the sum of those two and then bring the lambdas outside. And so this relationship, that's really, it just says that the bracket is a linear relationship. So it's a linear operation. Uh, it's really, if I do it on the other side, it becomes sort of antilinear or complex conjugate linear. If I do it over here, remember these have a complex conjugate in it, and so again I can distribute across and get psi 1 phi, psi 2 phi. But then when I pull out the lambdas, and the pulling those out, they pick up a complex conjugation sign. There's also some inequalities that are useful on occasion. One is the triangle inequality, which is this relationship. If I have a state psi plus phi and psi plus phi over here, then the square root of its absolute magnitude, this bracket, is always less than or equal to this psi bracket square rooted plus the phi state bracket square rooted. That's called the triangle inequality because in vectors it's pretty easy to show. It's related to the law of cosines really for a triangle. If I add this vector to this vector in terms of vectors, then the sum c is this vector here. And c, which is the sum of these two, is less than or equal to the squares of the two legs. Yeah? And it's equal when the angle between them is 90 degrees in the case of vectors. Yeah? In the case of linear inequality, the times that they're equal up here is when we have linear when one has linear dependencies between psi's and phi's. Yeah. Another one that'll turn into be of some importance for us is the so-called Schwarz inequality. And that's this expression. Again, it's equal if psi and phi are linearly dependent on each other. And that's a little bit different. We'll come back to this one. We'll prove this in some detail a little later on, but we'll give at least a plausibility argument for it. And then there's some terminology that I think should be pretty obvious. If this bracket between psi and phi vanishes, then we say that psi and phi are orthogonal to each other. On the other hand, if we have that psi and phi is equal to 0, and at the same time the bracket of psi with itself is 1 and the bracket of phi with itself is 1, then we say that psi and phi are orthonormal to each other. So that pretty much carries through. Let's look at the which one was it? It was number, I guess it was number 4 here, particularly the second one, this one here. And we might take a look at that and give sort of a plausibility argument that we have this expression was in that as one of the properties. And what I can do is first of all, simply do the following, namely, this is a complex number in general, and I know this complex number. I can interchange the order of these, but it's the complex conjugate, and that's you're really using this property number 3 here. Interchange the order, they're equal when I take the complex conjugate. So that's all I've done here is I've used property 3. And then I can, with this, it's a linear operator, so I can expand this as lambda times the bracket of phi psi 1 and lambda 2 times phi psi 2 inside the complex conjugation. And now then do a complex conjugate on all of these. And when I complex conjugate, I'll get the complex conjugate of lambda 1, complex conjugate of this one, complex conjugate of lambda 2, complex conjugate of this one. And then I use property number 3 again to switch these back. Switch the order, I take a complex conjugate of it, and I get a complex conjugate of the complex conjugate, I get psi 1 phi. And likewise here, when I switch these back, I'll get a complex conjugate of this, which neutralizes the first one, and so I get this term. And so that essentially shows that the two are equal. I used this pretty heavily, and you might say, well, how do you know that? So let's take a look at that. And the way I would do it probably is I'll just note that the this quantity phi times psi is equal to the integral. It's the sum over all the components of phi star psi. So that's really can be thought of almost as the definition of that bracket. The inner product is the sum over all components of psi of the first component, the first part complex conjugated, and then summed over all, a continuous sum over all of these i's, these components. And now then I'll take the complex conjugate of this whole equation up here. Complex conjugate of this side is going to be equal to complex conjugate of this side. And now these are, x is a real number, so I can take the complex conjugate of what's inside here. So I'll get the complex conjugate of the complex conjugate. And the complex conjugate of this one is psi. And if I replace I by minus I and replace I by minus I, I'm back to where I was to begin with. And then I've got psi star psi. And then I just reorder it. And this is nothing more than what you mean by the bracket of psi and phi. And so we've showed that this complex conjugate that was of this quantity with the order reversed is back to where we started. So that was that property 3. We can give you a plausibility argument for the Schwarz inequality, and we'll have to probably prove this in more detail a little later on. But for vectors, it's a fairly obvious relation. Because if you recall, let's just look at real vectors. The dot product or the scalar product could also be written as the magnitude of A times the magnitude of B times the cosine of the angle between the two. And if I square both sides of this, I square this side and I square every term on this side, I get this. But the cosine squared term is always between 0 and 1. Right? So if I take the maximum value, then this quantity has got to be less than or equal to when I set this cosine squared at its maximum value, which is 1. And so since this is equal to this, which is less than this, then I have the following relation that follows really almost immediately. And depending on how you want to write it, you can now then do the analog thing. A dot B is corresponding to psi inner product or bracketed with phi, quantity squared, less than or equal to. Well, A is just the inner product of psi with itself, the first component, the first piece of the bracket, the bra. And then B is this one. So sort of by analogy, one's led into this Schwarz inequality. But like I say, that one is going to be important enough for us. We'll probably give a little better presentation on that, and a little more definitive proof-like demonstration of that a little later on.